All right, folks, I think we should get started maybe. And this is the plan for today on the screen here. I guess maybe you've taken a look at this. And if you happen to have somehow looked at the materials from the course from last year, this is basically the same thing we did. I chose not to change these last two exercises and to change the final project, in part because every time I introduce a new exercise, it seems to be much more work than I expected, not for myself, but for you, that often what seems like a simple idea for an exercise turns into being much more complicated, as we saw in the GeoPython part of the course with like exercises 5, 6, and a bit of exercise 7. Those were new, and they were seemingly simple ideas that turned into being much more challenging in practice. So we're sticking with the same basic idea from what I've done for the last couple of years, which is to introduce the idea of thermochronology for this last two exercises and for the last, I guess today's really the last kind of lecture thing, because next week we will still meet, but it's going to be more like just a work session. So there won't be a lecture because the two exercises are essentially covering the same topic. There is one thing you'll have to do that's a bit different for exercise 14 than for exercise 13, but that's pretty, it's not a big change, so there won't be a lecture. I'll just kind of show you what the differences are between exercises 13 and 14, and then we'll be here to help out with you guys getting those things done. So yeah, this is the kind of overview. I just want to go here to the course page for a second. And a couple reasons for doing this. One is just to show you the overview for the lesson today. So what we will go through is this basic concepts of thermochronology lesson. I'm not assuming that you know anything about what a thermochronometer is. So we'll introduce that idea and how those can be used to study tectonics and erosional processes. There's a couple additional sets of slides that are up on the website that I won't go through, but are things that might be useful for the final report, because the final report is going to relate to this topic of thermochronology and to the last two exercises. And so there's a bit more information here. In years past, I went through that stuff, but it ends up taking quite a lot of time. And I think you're able to sort of pick and choose through these slides things that might be useful for you in writing the final report. So we won't go over that, but then I'll go through this overview of the exercises 13 and 14 just to make sure that everyone has a clear picture of what's coming and what's going on. And the final paper description hasn't really changed. So that's information still up here down at the bottom of the list of lessons and things like that. There are some scientific articles that I've added here for the final report, and so when we get to that, I'll just show you those as well. But you can see lessons 13 and 14, as well as exercises 13 and 14, they're both up now. So if you even want to work ahead, you're welcome to start into exercise 14. If you read through, you'll see that the additional tasks you have from this week's exercise to next week is quite small, so it would be not a big deal to start into exercise 14 if you get exercise 13 done early. And frankly, I don't think exercise 13, if I remember correctly, it hasn't taken as even the full time today for some people to finish it in the past. That's not my expectation necessarily, but there have been people that have gotten it done within the time we had on the first day. The other thing is this week, Wednesday is a holiday. So I did not make a plan for us to have a work session on a different day this week. I think maybe we don't need it because we'll have Monday next week. It's basically a work session as well as Wednesday next week. So if there's anybody who's really concerned about not having enough time to work on this exercise, you can let me know and maybe we can sort out a time to have a smaller group meet, but it's a bit tight to make reservations for classrooms, at least during nice times of the day at this point, because most of the rooms are booked. So we won't meet Wednesday this week, but next week will be a kind of normal week. So that's what's going on, and I guess maybe I could ask, are there any issues with the exercise 12, the things that are like burning questions? As usual, we'll have time after I finish with my lecture part to answer questions individually about the exercise, but how is it going in general? Is everyone feeling okay about exercise 12? Getting there? Yeah, okay. So we will have time if there are questions to talk about that stuff. But for now, what we'll do is go here to introduce the idea of thermochronology. And there's a few reasons why we choose to introduce this topic here at this point in the course. I'm not a huge fan of introducing a totally new concept late in the course, but thermochronology is something that is quite, as you'll come to see, it quite nicely relates to a lot of the things that we've done at other points in the course. So what we're going to do is introduce the basic idea of what is a thermochronometer in the first part of the lecture, and then talk about this idea of a closure temperature, which will make sense, perhaps, once you know what a thermochronometer is. And the question in terms of why we would want to introduce this topic at this point has to do with landscapes like the one in the photo here. Thermochronology is something that's used to study long-term tectonic and erosional processes and to study the rates of these processes. So how fast do faults move, how fast is the Earth's surface eroded, and things that are in some ways related to what we've been learning. So we looked at hill slope diffusion, we looked at river incision, we looked at glaciers, and all of those things are acting on the Earth's surface to change its geometry. And in almost all cases, it's lowering the Earth's surface and removing rocks and sort of taking them to lower elevations. And so in mountainous landscapes like here in the Pyrenees, it's one of the ways in which we can try to study the rates of these erosional or tectonic processes over long time scales, meaning millions of years. So not like going to a river and collecting the sediment in the river to see how much erosion is happening over a short time scale, but something that integrates over much longer time scales. It's also related to a number of the equations that we've already met. So when we talk about thermochronology, as you can maybe tell from the name alone, it relates to temperature. And when we talk about temperature in the Earth, we have things like the plot here of geotherms showing how temperature varies with depth. And when we talk about heat transfer processes in the crust, there's heat conduction, which is basically a diffusion process. There's advection, so when faults move and carry rock of one temperature, to higher or lower elevation within the Earth, or lower or higher depth within the Earth, that advects heat. And so we have our advection equation and diffusion equation in here already. And so we haven't talked really about heat transfer in much detail. You'll play with a model for heat transfer in the exercise for this week and for next week as well. But they involve the equations that we've already seen. So it's also a nice way to bring together some of the things we've used in a slightly different context. And the other thing that relates in terms of the equations we've seen here is the idea of this goodness of fit stuff that we saw back in exercises 8 and 9 when we did the basic geostatistics. So we can come back to some of these things we've already seen to calculate things like the chi-squared value, to compare some age you predict from a numerical model, which is what we'll use this week, to some data set, which is what we'll use next week. So in the exercise next week, we'll load in data, and then we're going to compare the data we predict from the model to see how the two relate to one another and quantify their fit using one of these goodness of fit calculations. So we can do a lot of things we've already done in one nice application, and that's why I kind of like this as a way to bring things together at the end of the course. Now, to get into the idea of what is thermochronology, we can start somewhere that's maybe a bit more familiar, and I think most of you are familiar with the idea of geochronology. And in that case, we're basically just dating some kind of geological material. This is a very generic term, so it could refer to uranium lead dating of a zircon, one specific method to get an age, or it could refer to other relative dating methods. It could, you could be counting tree rings or looking at growth rates of lichens or whatever. There's many different ways in which we can date geological materials. And a lot of them relate to having some kind of radioisotopic chronometer. So some sort of radioactive isotope like uranium or thorium or potassium that decays, and then you can measure the daughter product to get a sense of the time that has passed while this isotope has been decaying. So I guess that's probably familiar, yeah? The difference between a geochronometer and a thermochronometer is mainly in terms of how you interpret the meaning of the age. So for geochronometers, we generally think of them as dating the formation of a material. If you date a zircon with uranium lead, you're dating the time at which that zircon crystal formed. So if that was a pluton, it's the time that this pluton crystallized and that mineral was formed from melt into a crystal. For thermochronometers, we're often looking at the time since a material cooled down below a given temperature. Now these two things can overlap with one another. So if you have some kind of volcanic deposit, you can form the crystal and have it cool down basically at the same time. So the geochronometer might give you the same age as a thermochronometer. But if you have a massive pluton, it may take many millions of years to, or could take millions of years rather, to cool down. And so in that case, the geochronological age might be a little bit different than the age of some system that gives you the time since the rock was at a temperature of maybe 100 degrees Celsius, because it takes a long time for the pluton to cool to that temperature. So the concept is in many ways similar. You're doing the same process. You're taking some radioactive parent and you're measuring the accumulation of a daughter isotope. But for thermochronometers, that daughter isotope will relate to temperature. And we'll see how that works here a little bit now. So we can start with a basic definition. And here we can talk about a thermochronometer as being some kind of radioisotopic system. So a radioactive parent isotope, a daughter isotope that's produced by radioactive decay, or it doesn't necessarily have to be an isotope. It could also be some feature in the crystal that relates to radioactive decay, damage from decay, and the mineral that contains this system. So, okay, nothing really really fancy here. In fact, this is not really any different than a normal geochronometer here. We have parent, daughter, and the crystal that holds the two. Oops. Now, when we talk about performing the analysis, there's different terms here, and I just put these in to give you some clarification if you're confused in reading through the exercise or something about what does thermochronology mean. You have the definitions here. And for thermochronometry, we're basically just applying or using a thermochronometer to understand some kind of thermal history of rocks, and thermochronology would refer to that thermal history itself. So these two things might not make a lot of sense at the moment, but we'll go maybe ahead, and then you've got the definitions here to come back to. And I think I'll just leave it there for right now, because we need to talk about how the thing works in general first. So the general aim in most cases, as I've already sort of mentioned, is to try to look at past rates of tectonic processes or past rates of erosional processes. And oftentimes the timescales we're looking at are millions of years. So these are things that aren't necessarily easy to study with other methods. What it relies upon, as we'll see again maybe a bit more later in the lecture, is linking some temperature in the Earth's surface or beneath the Earth's surface to a depth in the Earth. And then that allows us to figure out, okay, well, if this rock was down here at this temperature, which might be represented by the dashed line here, if it was down here at some time ago, we could figure out how long it took for the rock to come from this depth up to the surface. And again, we'll see a little bit more about how this works in what's coming up. But here's maybe a useful picture. And this is essentially how the idea of a thermochronometer works. You have some parent isotope here that's shown in gray, and it decays to produce some daughter product. That is the little white balls here. And for thermochronometers, there's basically two different behaviors that you can think of. One is the closed system, so this would be more like a typical geochronometer. You have decay of the parent isotope, it produces a daughter product, and the daughter product stays trapped inside the crystal. It doesn't diffuse out, it doesn't go away, it's just trapped in there. And so however long it takes for this amount of daughter product to accumulate, you can figure out from the decay constant how old this crystal would be in that case, because it's a closed system. The thing that's different between a geochronometer and a thermochronometer is this open system behavior. And that is a case where you have decay, you still produce a daughter product of some form, but the daughter product may not be trapped within the crystal. So if you have something like a helium alpha particle, so a helium nucleus that's produced by alpha decay from uranium or thorium, it's a very small atom and doesn't tend to occupy places within the crystal lattice, but rather get placed somewhere within the crystal. And as a result, at high temperatures, the helium can diffuse out of the crystal, and it can be lost to the environment surrounding the crystal. And so you get this open behavior where, because at relatively high temperatures, for instance, now you can see the picture here, the daughter product is mobile. It's not trapped in the crystal, and it can be lost and diffuse away, or if it's a damaged product in the crystal might repair the damage at high temperatures. So this is where the thermal part comes in. This is the behavior as an open system at high temperatures and as a closed system at low temperatures. And this is, as stated here in the title of the slide, this is basically the essence of thermochronology. And I guess, does the concept make sense here? Like, I guess, can you picture this idea? Yeah. I mean, you can imagine, for instance, that uranium lead is not a typical thermochronometer because lead is a massive isotope and it doesn't diffuse out of a crystal very easily. There is some concern that over very long time scales you can lose lead to diffusion, but for the most part, people look at uranium lead ages and they say that's a crystallization age because the daughter product is not mobile. If it's helium is very mobile. It's a noble gas for one, and it's also small, so it's easy to lose. Now, the transition between these two behaviors, so here now we're looking at a picture of depth or temperature. You can think of it either way. So this is Earth's surface maybe, and then this is going down to higher and higher temperatures or greater depths. And here is the concentration of the daughter product. And what you see is that daughter product concentration is low at high temperatures. That's because we have this open system behavior. So the daughter product, when it's produced, just is lost to the environment. And it's high concentration at low temperatures. But the transition here is not like a switch. It doesn't just suddenly start trapping the daughter product. And so there's this zone over which you transition from the open system behavior to the closed system behavior. And this actually makes using thermochronology a bit more complicated, because you have to consider that some of the daughter product might be retained when you're within this gray zone here of these kind of intermediate temperatures. So you're not high temperature, you're not low temperature, you're somewhere in between. And so some of the daughter product will be retained in the crystal. This region in here is called the partial retention zone, which probably, if you think about it, partial retention makes quite a bit of sense for what is happening here. We're keeping some of the daughter product, not all of it. And or you can call it the partial annealing zone. That relates to the repair of the crystal structure from one type of radioactive decay. And we won't really talk in detail about that today, for instance. So in terms of temperatures, this is basically going from the temperature where almost all the daughter product is lost to the point where almost all the daughter product is retained. That's the temperature range in here for the partial retention zone. And again, I think, at least to me, the name is somewhat intuitive. Now, what's useful for us as Earth scientists is often just to have some temperature that we can refer to as the temperature where the system behavior changes. So we know that the thermochronometer doesn't just switch from being totally open to totally closed at one temperature, but we can pick a temperature in the middle of this range, in the middle of the partial retention zone here. And as you'll see in the exercise today, and if you look at the papers that are related to the final project for the course, you'll see this idea of closure temperature come up. And the closure temperature is essentially the temperature that we use as a reference for where the system transitions from being open to being closed behavior. It's just a reference point, and it's important to be aware that, again, we don't just transition from one behavior to the other at this temperature, but it makes it easier to think about having a single point rather than saying, well, anywhere between 140 and 100 degrees, we have this transition zone. We might say, well, let's just pick one temperature in the middle, 120, and we'll call that the closure temperature, and that's an easy reference point. So it's a term that was defined in a paper in the 70s as the temperature of a thermochronological system at the time corresponding to its apparent age. And when I was a student, I read this sentence dozens of times, and it never really made a lot of sense to me. But if you think about it this way, that you have some age at the surface, and you want to say, okay, what is the closure temperature's meaning? Well, it's simply the temperature of that mineral when it was so many million years ago. So if the age was 5 million years for some crystal you measured at the surface, this was the temperature 5 million years ago for that crystal. That's maybe the easier way to think about it with an example instead of, this is just awkwardly worded, I think. Even though it is a perfectly suitable definition, I find it a bit difficult to understand even as a native English speaker. So I can only imagine it's not that much easier for you to understand if you're not a native English speaker. Maybe, I don't know, maybe it was written by someone who was not a native English speaker either, and it makes sense when you translate it to German or something, I don't know. So anyway, it's a useful concept to have this single temperature. But there's a lot of things that will affect this closure temperature. So it depends on which mineral you're looking at and which parent and daughter product, really the daughter product you're looking at in the mineral. But also the size of the crystal will affect the closure temperature. The chemical composition can affect it. So apatite is a common mineral that's dated, but there's different types of apatite. There's a fluorine end member, there's a hydroxyl apatite, there's some other one, chlorine apatite, and those all have slightly different chemical compositions that actually affect the the daughter product being retained within the crystal. And cooling rate's a big one. So how quickly the crystal cools will affect this temperature range as well. And so you can see a plot here then of cooling rates. And so this is essentially just how quickly is the crystal cooling down. So 1 degree per million years, 10, 100 degrees per million years. This would certainly be a pretty fast cooling rate. If you think about it, this would be going from 100 degrees to 0 in 1 million years. And if it's a volcanic eruption, that's not a very fast cooling rate at all. But for most processes in the Earth, if you've got rocks that are at some depth in the Earth that are being brought toward the Earth's surface, cooling at 100 degrees C per million years is usually related to some kind of fast tectonic or fast erosional process. So we have cooling rates here on the top, and then we have closure temperatures that are shown here on the vertical axis. And then there's a bunch of different thermochronometers here. And I've put a little kind of transparent box over most of it because you don't need to know all of the details here. But the idea is that if we look at one system, so this is the retention of helium within an apatite crystal, you see that at a slow cooling rate, the closure temperature might be something like 40 degrees. And at a cooling rate of 100 degrees C per million years, the closure temperature is about 80 degrees. And if you're interested, I can talk maybe individually with people afterwards about why it is that the closure temperature goes up. The explanation is, from what I found, a little bit, it's not that complicated, but I never seem to be able to articulate it very well in front of a class, so it's easier if I can sit with you and draw a picture or something like that. But anyway, what we see is for different thermochronometers, essentially across a whole range of temperatures, the faster you cool down, the higher this effective closure temperature is. So for instance here, we've got argon in hornblende, and you're at about, 470 degrees at 0.1 degrees C per million years, and then it goes up to 600 degrees at 100 degrees C per million years. So it's actually quite significant, and this does, if you're trying to interpret, all you have at the surface is an age, and if you're trying to interpret the data, you have to somehow think about, well, what was the cooling rate, because that will affect what temperature I'm trying to think that this rock came from. And that's one of the reasons why we're going to use this little numerical model that we use for the exercise for this week and for next week, is because we don't have to worry about the cooling rate. If we use a thermal model, the cooling rate comes out of the temperature model that we have automatically. So we don't have to assume anything in that sense. So we've seen a little bit of what a thermochronometer is and how it works. And now we can turn maybe just to the idea of what causes cooling. So these rocks are somehow cooling from the interior of the Earth toward the Earth's surface. And what is it that causes cooling? One of the most common things that, especially in areas where thermochronology is often used, which are mountainous landscapes, is erosion. So when you erode the Earth's surface, you essentially remove rock from the surface, and you expose rock beneath that. And essentially this causes exhumation of the rock from depth to the surface. So when a glacier flows down a valley, it's scraping away bedrock and removing material from the surface and exposing rock from depth to the Earth's surface. And over millions of years, this can lead to kilometers of rock being removed by rivers or glaciers or landslides or whatever that exposes rock from quite deep up to the Earth's surface. So this can basically happen in any tectonic setting. If you've got convergent, extensional, or strike slip tectonic setting, or someplace that's not tectonically active, you have erosional exhumation. There are lots of mountainous places where there is no tectonic activity today, or no significant tectonic activity. But we still have rivers there, and the rivers are still carving the valley and exposing new rock or bedrock from depth to the surface. And so basically we're removing material at the Earth's surface, and what the effect is, in essence, is to have something like rock uplift here. So what the rocks experience here within the crust is that as you remove the rock above them, essentially you're moving rock up toward the Earth's surface. Now, you could flip this around and think about it either way. You can either think of erosion as lowering the Earth's surface, or if you hold the Earth's surface fixed, what the rocks experience is that they're basically moving up toward the surface. It's a matter of the reference frame, and it's maybe a little bit not that intuitive to think about it as like the Earth's surface as being a fixed elevation, but that's often the way that we handle it with numerical models. We assume the Earth's surface is fixed or maybe varying in some way, but it's essentially not moving up and down too much, but rather that it's fixed and the rocks beneath that are being exposed. It's equally possible that you could think of the rock, at some fixed depth here. If the surface is lowering down toward that rock, it has the same effect, whether the surface is moving down toward the rock or whether the surface is fixed and the rock is moving up. It's just a matter of the reference frame. So does this make sense? Because it's kind of important for the exercise for this week that at least you kind of have some idea that this is essentially what we're looking at. If you think of some parcel of rock here, it ends up at the Earth's surface, and it basically followed some kind of pathway like this. So as the surface has been lowered, the rock, or either as the surface has been lowered or as the rock above this parcel of rock has been removed by erosion, essentially you're just exposing rock at depth to the Earth's surface. And so in this case, erosional exhumation would cause this rock to move vertically up toward the Earth's surface. And that's what we're going to play with in the exercise for this week. You can also exhume rocks or expose them to the Earth's surface from tectonics in some places. So if you have a extensional setting, some kind of normal fault here, just by the fault slipping alone, you can expose rock here at the Earth's surface. So you don't need any erosion in this case to have this rock. If it was somewhere here along the fault interface buried and the fault slips, you can then expose the rock to the surface without any erosion. Now, of course, this only happens in places where you generally have extensional tectonics. And it's not like when you have this that you don't have any erosion. So usually you have some combination of tectonic and erosion that would cause rock to be exposed to the surface here. But it's just another way in which you can expose rocks to the surface. And this, of course, causes the rock to cool down as it's exposed to the surface. If it's down here somewhere at depth at higher temperatures, then fault slips and it's exposed to the surface, it cools down. You can also have cooling, of course, in other ways. If you have some sort of magmatic activity, often you'll use some kind of geochronological system to come up with the age of crystallization of some magma or volcanic deposit. You don't often use thermochronology for this just because the ages are often very similar to other geochronological systems, and sometimes they're easier to deal with. So uranium lead dating is pretty standard these days and perhaps a little bit less labor intensive than some of the other thermochronometer methods. And you can have things like reheating as well, but we're not going to worry about that. So we can talk a little bit now for the next maybe 10 minutes or so about some of the equations that we need to deal with when we think about these ages related to some kind of radioisotopic system. So if you have some radioactive decay, this is the equation you can use to calculate an age. And this is assuming that there's no loss of the daughter product. So this is what works for typical geochronometer. And that is that the age you would get would be a function of the decay constant, so 1 over the decay constant for whatever the parent is. So if it's uranium, you pick your uranium isotope, and you can come up with what the decay constant should be there. And that's multiplied by the natural log of 1 plus the concentration of the daughter product divided by the concentration of the parent isotope. And this is a pretty standard equation for calculating ages related to radioactive decay, whether it's carbon-14 or uranium or whatever. But of course, for a thermochronometer, this doesn't work because the daughter product is not all retained, so it can be lost to diffusion. So we have to think about this solid state diffusion part of the system, and the equation there. And of course, that is a diffusion equation, no surprise. And what happens is normally with these isotopes that are produced for thermochronometers is they're things that don't go into the crystal lattice nicely. So typical, I gave one example already of helium in apatite or zircon, but argon is also another element. These noble gases don't find nice places in the crystal lattice. So if you have some crystal here that I've just shown generically with these blue dots, these are kind of normal atoms in the crystal lattice, and of course I haven't tried to make this actually any certain mineral or anything like that, but these are the things that are supposed to be there. So if it's if it's apatite, for instance, these would be calcium and phosphorus and oxygen and whatever. And then there's these parent isotopes that have substituted in as the crystal form. So these could be uranium or thorium, and here we have decay of one of those. So it's a spontaneous decay of some parent isotope, and that produces then one daughter isotope shown in green. And you can see that these parent isotopes are in the crystal lattice. The daughter products are not. They're just floating around inside the crystal. Now, of course, the crystal lattice does prevent them from easily just immediately going outside of the crystal. But they're able to diffuse because they're not within the crystal lattice. And we can use a diffusion equation for this. This is just showing you the change in the concentration of daughter isotope over time as being related to this diffusion constant. And here, the diffusivity or diffusion constant is temperature dependent. So it will be higher at high temperatures, so the diffusion will be occurring more rapidly at high temperatures and more slowly at low temperatures. Here's just the gradient, or the sort of changing the gradient of the daughter isotope with distance within the crystal. So this is, we've already seen this earlier when we talked about the diffusion equation. And then there's some P term, which is the rate at which the daughter isotope is being produced. We don't need to go into this in great detail, but if you go through doing the math here, you can come up with a relationship for what this diffusion constant looks like here, where we have this temperature-dependent diffusivity, and that's related to this value of the diffusivity at infinite temperature. It's sort of a theoretical value, the size of the crystal, and then there's an activation energy and gas constant and temperature dependence here. So again, you see E to the minus 1 over T, which means this will be sort of an exponential value. It's actually similar to how the strength of rock decreases with depth or other things like that. Very common form of exponential equation. The diffusion domain is typically the size of the mineral, so that's just what the A is there. And then the activation energy is the energy you need to put into the system to get the diffusion to occur at all. And so these are all things that can be measured in the laboratory from people who like to do these kind of experiments. And In the exercise for this week, you can look at the code and see the different values here. They're already in the code for you for different thermochronometers, but you can take a look and see kind of what typical values are here. Anyway, the point here is that the key idea for this daughter product being retained in the crystal or lost is related to this change in the diffusion with temperature. So it diffuses more quickly at high temperature and much more slowly at low temperature. You can sort of see that here. So this is showing temperature versus time, and then along the bottom here it's showing the ratio between the daughter and the parent isotope versus time. And what you see that as you go from high temperature down to low temperature, you have first this kind of TO, the open behavior. So this is the temperature at which, or above which, none of the daughter product is retained in the crystal. It's all lost by diffusion. TC we've already seen, that's the closure temperature. And then TB is what's sometimes called the blocking temperature, where all of the daughter product is being trapped within the crystal. And so you can see the ratio of the daughter product and the parent along the bottom. It's basically 0 above TO, and it's a linear relationship above TB, and then there's this transition in between. And if you just take this linear relationship and extrapolate it down to where it intersects the time axis, that's what gives you the time TC that corresponds to the temperature. So don't worry about too much the details here. I mainly put this in for the sort of sake of completeness and understanding the different behaviors, but it's not so important. So one thing that's going to come up in the exercise, both for this week and next week, is this equation from this 1973 paper by Dodson for calculating the effective closure temperature. And that was done using this idea of temperature-dependent diffusion and trying to figure out the temperature at which the system began behaving like a closed system. And there's a bit of detail here that's not critical for dealing with the exercise this week, but basically the idea here is that we have this same kind of diffusion relationship where the diffusivity is related to the diffusivity at some infinite temperature, and then e to the minus t over tau, and this relates to the time it takes for the diffusivity to decrease by a factor of 1 over e. Again, I'm not going to spend a lot of time on this because I don't think it's critical for the exercise for this week. But if you want, you can kind of follow or look through the slides, and what is sort of important is this equation for calculating the closure temperature. And so here you can see now this activation energy that was part of the equation about the temperature-dependent diffusion. Activation energy is in here. A is some geometry factor, and that has to do with what the shape of the crystal is, whether you can treat it like a sphere or whether it's like a cylinder or a plane sheet. So like micas are often treated as kind of planar sheets. This is the tau that is related to the diffusion constant, and then d naught is the diffusivity at infinite temperature, and then A again is this size of the crystal. If you're starting to get a little bit mixed up with the different letters and things like that, don't worry, you'll have time to look at this in the exercise. But essentially, if you know these things, you can calculate the closure temperature. And for the most part, we know EA because that will be something that's a property of the daughter product in the crystal. We can choose a value for A based on the shape of the system we're dealing with. D naught would be something that's known from laboratory experiments, and A is the size of the crystal, so you can also know that. The only thing we really don't know is this tau, and the equation for that is up here. And again, it has EA in it as well, the activation energy, has temperature in there, and it has the cooling rate. And so this is where, basically we calculate this value of tau here. The T that's here is basically the closure temperature. And you can see that if you have closure temperature here in the equation for tau, and you have tau in the equation for closure temperature, you don't know both of those things at the same time. And so we'll talk about how you handle that when I talk about the exercise for this week. But essentially, this is mostly stuff that we have available. So calculating this closure temperature is something that can be done relatively easily. And I'm going to skip over the pseudocode thing about Dodson's equation for right now, because we'll come back to that in the preview of the exercise. But what you can do with it then is you can make plots like this of the cooling rate and calculate what the closure temperature is as a function of the cooling rate. And you can see again this kind of effect of closure temperature going up for faster and faster rates of cooling. So this is basically straight from Dodson's equation for helium inside of an apatite crystal. And you could reproduce this plot with the exercise for this week if you want to. We won't do that, but you could if you were interested in doing that. And with this equation, we have the closure temperature, and we can calculate the closure temperature as a function of the cooling rate, but that doesn't necessarily tell us about any kind of tectonic or erosional process. So we have to have some way of relating this closure temperature to some depth in the Earth if we want to start talking about rates of processes. So we could assume that temperature increases in a straight line with depth. So let's say it is, increases 20 degrees C per kilometer. If you know your closure temperature is 100 degrees C and you assume it's 0 at the surface, you could say, okay, well, this closure temperature is at 5 kilometers depth. The thing is that that's not often the case, that we can assume the temperature increases linearly with depth, and we can do a bit better, and that's what we're going to do for the exercise for this week. And I think I'll skip the recap because I've already kind of gone a bit longer than I intended. So I won't make you deal with these questions, but the basic idea for thermochronology, as we've seen, is it's a way for us to date time since a certain rock was at a given temperature. And so it relies on a daughter product in the crystal that is not permanently trapped within the crystal, but diffuses out of the crystal at high temperature and is trapped at temperatures below this thing down here, the closure temperature. So this effective closure temperature is just some temperature we can choose in the middle of the range of temperatures between where the daughter product is completely lost and where it's completely retained in the crystal. And it relates to the cooling of the mineral sample in the sense that as you cool more and more rapidly, this closure temperature goes up. And again, I can explain that if people are interested individually. I can expand on that there. So that's the main part of our lecture. I'm going to introduce the exercise next, but I thought maybe I'll ask, are there any questions, or was that somewhat clear what this thermochronometer idea is?
Yes.
Yeah.
There is related to tau. What's the name for tau? Like, what the Greek sense?
Well, yeah. So it's did I give it a name? I mean, it's the time it takes for the diffusivity to decrease by a factor of 1 over e. So it's it relates to the time scale of, well, maybe I can show it here. So in the plot here, you see that we just kind of take this line and extrapolate down to where it intersects the time axis to get this closure temperature. It has basically to do with, if we assume that as the cooling rate changes, that will determine the change in the diffusivity of the daughter product, right? So as the thing is cooling down, it changes the diffusivity, and this has to do then with the time scale over which that decrease happens with basically 1 over E. So it's related to the natural log of the time scale of the change in diffusivity. So maybe not the most clear definition, but that's, if you look at the the equation for it, you can kind of see that as well, that it depends here on this cooling rate and the temperature itself. And so as the cooling rate decreases, for instance, then the value of tau is going to, well, it's maybe not that intuitive to think about it this way, because I won't say more about that because I think I'm not going to say it clearly. So are there other questions about this thermochronology idea? So for the lesson for this week, just to go back here, there are additional slides here about low temperature thermochronology. That's really what we're going to focus on. And then also about quantifying erosion with thermochronology. That also relates to what we're doing for the exercise for the next 2 weeks. I'm not going to present those things, in part just because it tends to be quite a lot of material to take in at once. But if you're interested, the lecture slides are up, and so you can go there and take a look at some different thermochronometers based on diffusion of argon or helium or fission tracks in apatite. You can see their temperatures, and you can see essentially the main idea of how these different chronometers work in the lecture slides there. So like here, for instance, it goes through a little bit of the detail of how helium decay or uranium decay produces helium, and then how that relates to the behavior of this thermochronometer. Also talks about things like fission tracks, which happen as a result of spontaneous fission of uranium-238. So you can go there and see a little bit more details about the methods if you're interested in that. It might be helpful for the final project, but I think less is more in terms of getting to working on the exercise this week, and so I don't want to bury you with that stuff. But you can also go and similarly see some things about how you can quantify rates of erosion with thermochronology in the other set of lecture slides that are up. So those are on the course page already. There's one other thing that I was going to show you, and that is that there was the doctoral program here had a course on thermochronology that was maybe, I don't know, 5 weeks ago or something like that. On the course page, we had a group of invited lecturers that came and gave lectures about different thermochronometers and things like that, and also myself and Ilmo Kukkonen gave some lectures about thermochronology. I will put a link on the page for the lesson for this week to this page if you're interested, because all the lecture materials are available online for that course as well if you're looking for kind of more information. For instance, on like the argon-argon thermochronometer, there's a whole bunch of stuff here, and it might be a little bit easier than going searching and like reading articles from scientific journals. So there's stuff on fission track dating, and there's stuff on using uranium, thorium, and their decay to helium in different systems. So you can go there and you can find the lecture slides and play around with that stuff if you want to get some more information. And so yeah, I will add the link to the lesson for this week, and I'll probably throw it in for the lesson for next week as well, just because it might be helpful for getting more information if you're curious. So any other questions, or shall we move to this preview of what's happening with the exercise? Yeah, let's go there. All right, I want this one. So for the next 2 weeks, the exercises are quite related to one another, and they all relate to this idea of thermochronology that we've just introduced. And in the exercises, we're going to be using some data, not this week, but next week, from the Himalaya in Bhutan. And well, this is just a good excuse to put in a nice picture of Bhutan. It's a scenic place, as you can tell. And the data that we're going to use are from a paper in 2014. We've actually already used this data once back in exercise 9, maybe? 8 or 9, one of those two. So you've dealt with this stuff once before. And this is data out of the western part of Bhutan. So here is a map of where we are in the eastern part of the Himalaya. And there is this data that was collected within this region in western Bhutan. A whole bunch of rock samples that were collected and dated with different thermochronometers. So at the time we dealt with this stuff back in exercise, I think it was 9, we didn't know what thermochronometers really were. Maybe you still don't, but hopefully you have some idea of what a thermochronometer is here. And our goal in the exercise is going to be to interpret this data and to take some of these ages we have at the surface and try to relate them to rates of erosion. And so anyway, this is where we are geographically, and you can see we're using apatite and zircon as the minerals, and either looking at the accumulation of helium or these damage tracks from decay of uranium by fission in apatite and in zircon. So that's our data, and it looks something like this. So if we take the data and plot it as a function of latitude, maybe some of this is starting to look familiar, or kind of come back to you now, because I think essentially what we did was make a plot not of all of this data, but of some of this data for one of the exercises, 8 or 9, I can't remember which. But we plotted it as a function of latitude. So you had this age, and there was the error bars, and you made the plot of the ages as a function of latitude. It didn't have this swath of elevations in there, and I don't recall which color dots we were using. I think it might have been the pink ones that we were plotting, but I don't really remember. Anyway, the point is we have a lot of data here, and if you look at it, it's a bit noisy, and so the interpretation here in terms of trying to say, okay, what's the rates of erosion? Well, it's not that obvious, but we're going to try to interpret these ages to give us some idea of how quickly are the mountains there eroding in Bhutan. And anyway, so here, this is not Bhutan, this is the Tetons in Wyoming, but just to give you the definition of this word exhumation, normally when you talk about exhuming things in normal society, it's like exhuming a body to be, I don't know, looked at for signs of some weird thing, or to check and see if someone's ring is missing or something. I don't know. You don't talk about exhumation often in other terms, but for us, it means removing rock above you. If you're some parcel of rock sitting down at some depth in the earth, if rock is eroded above you, you're being exhumed. You're moving toward the earth's surface because rock is being removed above you. And this happens as a function of erosion, but it can also happen as a function of tectonics, as we saw in the lecture earlier. With you have normal faulting, you can exhume rocks from depth to the surface that way. Now, if we want to use thermochronology to study the rates of exhumation, we have to come up with some way of calculating that rate. And I already alluded to this earlier, but one of the simplest ways we could do it is assume that the temperature gradient is constant. And if we have a constant temperature gradient, so constant increase in temperature with depth, and we know the closure temperature, we can figure out what that depth would be when we were at a certain temperature. So for instance here, if we had an apatite crystal with a helium age of 12.3 million years, and we assume that the closure temperature is 75 degrees and that the geothermal gradient is 20 degrees C, how would you calculate the rate of exhumation? The easiest way is you just take the depth. If you can calculate what the depth is, and you divide that by the age, and that tells you, on average, how quickly this rock came to the surface. You don't have any information about, it may have rocketed up to 50 meters below the surface and then sat there for 10 million years. You don't know that. All you know is that, on average, it was at this depth, and now it's at the surface, and it took 12.3 million years to get there. So you can take the depth and divide that by the age, and that gives you an exhumation rate. That's pretty easy. I've already mentioned that this sort of, the math is sort of spelled out in more detail here. And if you do it, you take 75 degrees C divided by the geothermal gradient, that gives you the depth. You take that depth and divide by the age, and it gives you an exhumation rate of 0.3 kilometers per million years. And I've said this probably before in class, but if not, just as a helpful reminder, often you'll see things reported in millimeters per year or centimeters per year. A millimeter per year is the same as 1 kilometer per million years in terms of the way the units work out. So you might calculate things in kilometers per million years, and I might ask you to report them in millimeters per year. The number is exactly the same. So you could go through the process of doing the conversion, but I'll just tell you that it'll save some time if you don't have to do that. So the thing is that using a geothermal gradient that is linear or constant with depth is not a good idea, because we know in many cases that geotherms are not straight lines, and so they're curved instead. And if you ignore this curvature, you can be quite off in terms of calculating exhumation rates. And so a better idea is to use some kind of thermal model that can account for the fact that the geotherm is curved, and then you can find your closure temperature in the thermal model and get a better estimate of what the depth is. So here's a typical geotherm in continental lithosphere, so going from 0 to 1300 degrees at 130 kilometers depth. And you can see obviously that it's not a straight line. And it might look somewhat straight up here, but the curvature is more or less across the whole depth range. And the equation we're looking at is just plotted here. It's sort of simple solution for constant uplift rate at steady state with a fixed temperature at the top and a fixed temperature at the bottom. But advection is important. So if the rocks move up toward the Earth's surface, this is one of the ways in which you bend the geotherm. So if you have erosion at rapid velocities, that tends to cause rock to be moving up toward the Earth's surface, and that will bend the geotherm, as well as heat production by radioactive isotopes like uranium, thorium, potassium. They contribute to heating rocks by radioactive decay, and that also causes this bending of the geotherm. That's a whole kind of course in itself if you want to go into the details of that, but for us, the point is that this is not a straight line, so we shouldn't use a straight line. So we know how to calculate exhumation rates, but in order to do this and to figure out, at what time and at what depth was I at when I passed through the closure temperature, we have to generate a cooling history for a rock sample. So if we have a thermal model that can make a nice plot like this of how temperatures vary with depth, what we want to know is how does some rock travel along this line toward the Earth's surface, and at what time is it at different temperatures. And so that's where the cooling history comes in. And we know the surface sample that we collect at the Earth's surface today might be at some depth like z equals 0. So if we assume there's no topography, we'll just say it's a flat Earth, not like the Earth isn't round, but like the surface is flat. Then we'll just say z equals 0 as our reference point for where our rock sample is collected. And we have this velocity of advection that we can use then to calculate a cooling history. And the way in which we can do that is we can figure out, okay, well, if we know the rate of advection, let's say it's a millimeter a year that we're moving rock up toward the Earth's surface because it's being eroded down at that same velocity. We can say, if we go back in time, if it's a millimeter per year, that's 1 kilometer per million years. So a million years ago, this rock would have been 1 kilometer deeper in the Earth. 2 million years ago, it would be 2 kilometers, and so on and so forth. And we can just figure out, okay, now we know at what depth the rock is at these different times. And if we know what the depth is, and we have a plot like this, for instance, of how temperature changes with depth, we can also say what the temperature was in the past. And maybe it makes a little bit more sense if we look at something like the plot here. So we might have some rock that starts down here at, I don't know, 70 kilometers depth at some time. And, you know, here we have its depth and temperature at this temperature T1. And then sometime later, it's moved to a shallower depth because it's being advected upward or moved toward the Earth's surface. And now it's still along this blue curve, but at a lower temperature. And as you continue, you can see the different times until you end up at the Earth's surface. And because you have this temperature history, you can figure out basically where and at what time did you pass through this dashed line here, which might be the closure temperature for the mineral. And then if you know when that happened and you know what depth it happened at, you can then calculate the rate of exhumation. So that's the general idea of what we're going to do in the exercise this week. Is we're going to use a thermal model to calculate thermochronometer ages, and the thermal history you'll see is calculated in a similar way to this. It's not exactly the same as what's shown here, but it's quite similar. Conceptually, the idea is basically the same. The difference is that we're going to use a temperature calculation that's not steady state. So this is a steady state solution. It doesn't change with time. What we're going to use will change with time. And you'll see how that works in the exercise. Yeah, does this make sense, or are you totally confused about what this plot is showing? I'm not getting a kind of good sense that you're totally with me on this. Almost, okay. All right. Oops, I've gone the wrong way here. So let's go back here for just a second. I think everybody was with me up until this point of calculating this exhumation rate. When we assume that the temperature increased linearly with depth, we found out, you know, how deep is the closure temperature, and then we just said, okay, well, if we know it's that deep, then we can just divide by the age, and that gives us the exhumation rate. I think everybody seemed to be kind of following that part. The thing is that when we don't have a straight line for the temperature, we can't just calculate what depth a certain temperature is at, because we don't know the relationship easily of how depth and temperature are connected to one another. So because we don't want to assume that temperature increases in a straight line with depth, it's better to use some kind of thermal model. But if we use a thermal model, we have to then figure out some way of knowing how the rock cooled in order to figure out when it passed through the closure temperature. So if the rock parcel starts out at 50 kilometers depth and you're eroding at the surface and this rock is moving up toward the surface, we just basically have to record what is my temperature at these different times as I'm cooling down in order to figure out when does the rock go through the closure temperature. So that's the kind of key thing that's shown here. Is basically the idea of recording your temperature at different depths as the rock is cooling down. And if you record this, then you can figure out at what time do I go through this closure temperature. And if you know that, because here we record for this point its depth and temperature, you can also figure out at what depth was I at when I went through the closure temperature, and you can use that then to calculate this exhumation rate. It doesn't need to be crystal clear right now because you're going to do this in the exercise and you'll get to play with the code, and maybe you'll actually, it might be better that you learn by playing with it than for me to sit here and come up with 10 different ways to explain this. But the general idea, I think, is that we can't just calculate what the depth is because we don't know how temperature changes with depth if we don't assume it's a straight line. So what's going to happen in terms of the age prediction is we're going to calculate temperatures. We're going to use a thermal model for this, and it's already set up in the code to work for you. And with the thermal model, we're going to then calculate this temperature history. So we're going to have an advection velocity, and we're going to calculate what is the temperature at these different depths and record that. And we're going to use that for two things. One, we're going to use it to calculate what the closure temperature is, because the closure temperature, we're going to use this Dodson's method where you calculate it based on the cooling rate to figure out what is the closure temperature, and then we're going to record the time when the rock cools through the closure temperature. So that's basically the predicted age. And if we have that age, then we can figure out what the exhumation rate is quite easily. We're going to then compare the age we get from the thermal model to ages from the Himalaya and Bhutan, and essentially use this goodness of fit statistic to give us some number of how well do these two things compare, and you'll go through and kind of tweak some of the numbers in the numerical model until you get a good fit between the predictions and the observed ages in Bhutan, and that will allow you then to get a sense of what the exhumation rates are on average. Again, we're going on about an hour and a half of me talking nonstop, so I think even if we're following for a while, maybe you're starting to fade at this point. So let's go here. We'll take a quick look at the exercise for this week, and I will maybe also just mention what the exercise is for next week, but I'd like you to have some time to get started, so I need to stop talking here shortly. So the exercise for this week, I think I've kind of already explained the concept in a bit of detail, but we're going to deal with thermochronology, and we're going to use a numerical model for calculating temperatures, and then also calculate closure temperatures for different thermochronometers, and in the end, for the exercise for next week, compare some predicted ages to ages that are observed in the Himalaya and Bhutan. So we're going to use a solution to the heat transfer equation that depends on time, and it looks like this. And as you can see here, hopefully the important thing is perhaps here, and that is that you don't need to put this into Python because it's not that nasty, but there's a lot of parentheses and things like that, and you'd spend probably an hour trying to get your parentheses to match up, and it's just not necessary. So this is already in the code and it works, and you have I wouldn't mind if you look through the equation just to kind of see what some of the terms are here, but it's not super important for the purposes of the exercise because you'll be able to run the model and see what the plots look like right from the start. But anyway, things that are in here, obviously there's time. Vz is the advection velocity, so that's essentially how quickly the material is moving vertically up. Kappa is a diffusivity for temperature, and otherwise there's depth, and G is the initial temperature gradient. And then there's this complementary error function thing here, which we've not seen, and probably you've not seen maybe ever. But its definition is down here. It's not that important. There's a Python function that does calculate the complementary error function for you, so you also don't need to worry about doing anything with that. But I just showed it here so that you kind of know what it looks like. And if you're curious, there were some notes in lesson 11 about solving the advection diffusion equation. If you kind of want to see how those things link to one another, that's essentially what is solved here. This is a solution to the advection diffusion equation for a time-dependent case. The steady state case is what's in the notes from lecture 11. If you're interested in that, you can read through those and see how that works. But for the exercise for this week, there's a starter script called agepredict1d.py, and if you run it, it makes a plot like this. And so one of the first things you have to do is add some axis labels. As it turns out, this is depth and this is temperature, so this is plotting a geotherm. And the important thing here is that this blue line at 50 MA, when I'm talking about MA here, I'm talking about time in the past. So this is 50 million years ago, and then this is the temperature today. So just so you're not confused, if you flip those things around, it will be kind of difficult to understand how this equation works if it goes from having a curved geotherm to being a straight line. That doesn't really go with what I just explained. So anyway, if you run the code, it makes this plot of a geotherm that looks like this. That should work straight from the start. And the only thing to watch out for is just the names for the time. So 0 MA is meant to represent today. When we deal with thermochronometer data, the reason I do this is because the age is always going to be some kind of age in millions of years, and that's always millions of years ago. So it's easier to relate the model to the ages this way. Anyway, you're going to use the code. You're going to go through and play around with some of the things like changing the velocity of advection, changing the time over which the solution is calculated, and things like that, to get some idea how this equation works. And this is sort of explained in a bit of detail in the exercise, so I don't need to go through that. The next part is related to this, using the Dodson's equation to calculate the closure temperature. And we've already gone through this as well in the preview of the exercise. This equation is also in the code already for you, so you don't need to worry about coding this up. In concept, it's not that challenging, but it's a little bit tricky in terms of the code implementation. So anyway, we have that here, and it's already in the lecture slides and in the code, so I'm not going to spend any more time, although you certainly would encourage you to read through this part of the exercise just to make sure you understand. So what you do in problem 2 basically is turn on calculation of some different thermochronometer ages in the code. And you can then see, in part 1, you see how the thermal model works. In part 2, you see how the cooling ages, the thermochronometer ages, change when you change different things in the code. And so again, it's going to be kind of turning on different functionalities in the code, and then there's some questions there. I think in all you're going to produce 7 plots in problem 1 and 4 in problem 2. You make a lot of plots, but you don't really need to do that much work to make the plots. Part of the reason why I want you to make a lot of plots for the exercise this week is that you can put them into the final report thing, and so it's nice to have a bunch of them to choose from, so you can kind of pick the ones that you think are most relevant for what you end up saying in the final project report. So you're going to make a bunch of plots, and you can see there's not a lot of other questions here. The point for the exercise this week is essentially to produce things that can go into the final report, not to spend hours and hours tinkering with the code, and I want you to get some results kind of quickly and be able to think about this final project report a little bit more. So that's the exercise for this week. The one for next week is quite similar. The only difference here is we're going to load in a data file, and then you have a sort of similar starter script. You're going to load in a data file that has some ages in it, and then you're going to compare the ages in this data file to the ages you predict with the numerical model, and you'll use that using the goodness of fit, or do that with this goodness of fit equation that's shown here. And the only other significant change is you're going to have to add in a subplot so that you have two plots in the same window. And we've done that before, so hopefully that's not too much of a big challenge. So that's the first part. In the second part for next week, and again, I can go over this a little bit briefly on Monday next week. The second part is where you try to fit the data. You try to get the good, or sort of smallest goodness of fit value between the observed ages and the predictions. And that will allow you to then get some idea or an estimate of the rates of exhumation. And again, you'll produce a bunch of plots. There's not too many other questions, and then that stuff can go into the final report. So those are the exercises. I've taken more time than maybe I had intended, but next week we won't really have much to say at all. Just to remind you, the final paper information is up. We've already sort of shown this once, I think, to one of the Wednesday groups, I think. I don't think it was during lecture time. It was during the Wednesday work session. But you've got something like 6 to 8 page long paper to write as the final thing in the course, and it takes a lot of the plots from exercises 13 and 14 and just puts them into the context of some kind of scientific article. So I sort of try to spell out in some detail what each section should contain, so you can read through this to see what the paper is all about. I also include a little table here of how your grade will be determined on the paper, so you can see what each section should do and try to make your paper do those things. So this stuff has already been up on the course page for a while. The one thing I added that is useful for you is there are some links to some scientific articles here. I think I asked you to cite at least 5 articles in the paper, and there are 6 here. So I'm not making you go find articles. You're welcome to, and if you're curious to look into literature and find some other things to cite, I always enjoy it when I read a paper where people have gone and found some other things. But these are really quite relevant articles that will be helpful for you in writing the final paper. So they're here, and if you click, you just get a PDF of the articles, and I've tried to choose some. I mean, these 2 from Bhutan are that you're going to have this data in the exercise, so you're going to want to probably cite these at least. There's some papers just in general things about the Himalaya. If you're for the geological background section, for instance, you might want to say a little bit about the geology of the Himalaya, and these are good review papers. And then there's some things in general about thermochronology. So, yeah. Are there any questions about the exercises for the next 2 weeks or for the final paper? The tentative deadline is the 22nd of December. That is something I'm willing to be flexible about in terms of the due date for the paper, but I would much prefer to talk about that in advance rather than getting an email at midnight on the 21st saying that there's no way you're going to have the paper ready. I don't really respond as nicely in that situation. So maybe we can come back to this next week maybe you'll have some idea of like how things are going with the exercise and what's, what you're going to have to do for your other courses. We can talk about whether this date is going to be something that's reasonable or whether you prefer to have some extra time. I really don't mind so much as long as it doesn't go into period 3 too far, because then that starts to mess with your other courses. And that's not good for you. It's also not good for me to have too many things kind of hanging over from the previous term. So we can come back to that. But otherwise, if there aren't any questions, I've again talked for much longer than I intended to, but you're free to get started with this exercise 13, 14, or ask us questions about exercise 12, or I guess anything else. So have at it.
By the way, when is this week's practice?
Yeah, so I mentioned it that we don't have one scheduled for this week because of the holiday on Wednesday. Yeah. I was going to say that, if people want, we can try to arrange something with a smaller group, but I wasn't planning to find another classroom. It's a bit tricky to reserve one at this point. I guess the thing that relates to that is next week on Monday, we basically won't have a lecture. I mean, we'll be here, but it'll more or less be like a regular work session. So there'll be time next week on Monday that in some sense would take the place of the Wednesday session from this week. So exercise 13 and 14 are already up, as well as there really is no lesson 14, but all that stuff is up on the webpage already. And so next week on Monday, I'll again just highlight a couple things that are different in exercise 14 if people haven't looked at it, but otherwise you'll basically just come and work. So if you're already done with exercise 14 by Monday next week, for instance, you don't need to come at all. But if you're still working on exercise 13 and you want extra time, then Monday is basically going to be like a regular work session. So that's the plan. If there is a need, we can try to find a time to have a smaller group meet somewhere, but I wasn't planning to reserve a classroom.